Good afternoon. My name is Chuck Smythe. I'm the Director of the Culture and History Department here at Sealaska Heritage Institute. Welcome to our first lecture in our series this fall. We're excited to have two speakers splitting the hour. And I want to remind you that there will be time for questions at the end of the speech, at the end of the talk. And also, people online can submit questions via chat, and we will retrieve those and read them. So today's lecture is entitled Our Submerged Past Project, Exploring Inundated Late Pleistocene Caves on the west coast of Prince of Wales Island with SUNFISH. The first speaker is Dr. Kelly Monteleone. Her talk is entitled Submerged Archaeology on POW Island. Kelly Monteleone is an underwater anthropologist with Sealaska Heritage Institute and an adjunct assistant professor in the Department of Anthropology and Archaeology at the University of Calgary. She has a PhD in anthropology from the University of New Mexico and a master's in maritime archaeology from the University of Southampton, United Kingdom. Her research focuses on providing the tools and expertise to help locate submerged archaeological sites on the continental shelf of Southeast Alaska and assist the local communities in learning more about their ancestors. The second speaker is Dr. Christoph Richmond of SUNFISH, Inc. His talk is entitled Advanced Robotic Mapping and Exploration in Southeast Alaska with the Autonomous Underwater Vehicle known as SUNFISH. Dr. Richmond is the Chief Technology Officer of SUNFISH, Inc. He became fascinated with marine robotics when working on automating some capabilities for remotely operated vehicles at the Monterey Bay Aquarium Research Institute. He has a PhD from Stanford University in visual mapping, navigation, and control systems for ROVs. He's taken advanced, highly maneuverable underwater robots into all kinds of places, from caves in Namibia to under the McMurdo ice shelf in Antarctica. He has been involved with the development of the underwater vehicle SUNFISH from its beginnings. If I may remind you to turn off your cell phones, and we may begin. Thanks, Kelly.
Thank you so much, Chuck. Pleasure to be here today. I'm going to start stuff off. I'm Kelly. I'm going to talk for a little bit about the background for the project and year one, and then I'm going to pass off to Christoph, and he'll introduce himself then. And then I'm going to come back and talk a bit about the results of some of the stuff we did in year two. I'm going to move Christoph off the screen for a moment. And so what I want to point out before we move on is this is a NOAA Ocean Exploration funded research project. And so this is meant to be one of our final presentations for this grant. And so Christoph and I are presenting. Note the image is reversed. I flipped it, and it looked so weird to have the ship reversed with the wheel on the wrong side. I just couldn't do it. So, you know, you got Christoph and I looking at the screen on the boat, but that's as good as I could do. And the QR code on the bottom is actually for the NOAA site for this project, and that includes some really interesting little pieces we've put together. So, I get to talk first, and I'm going to talk about our submerged past. So to introduce myself, I'm third-generation Canadian with ancestry from Italy and the UK. As Chuck mentioned, I see my role as to provide the tools and expertise to help locate Indigenous cultural heritage that's currently on the underwater, and also terrestrial archaeology can occur. I just like underwater better. But what I found is it's not just me talking. I may be the one up here, but there's a huge list of names that needs to go with this. This is work from many people, and it's never really done in isolation. So this is our research team, and I believe that list is missing Rosita, actually. Interesting. So what am I talking about? When push comes to shove, the question I'm trying to answer is, how and when did people migrate to the Americas? When did this happen? When we talk about this, there's really 5 different routes people could have taken. We've got transatlantic, North Atlantic, trans-Pacific, and then I have a strange feeling most of you were taught about people walking across the Bering Land Bridge and down the ice-free corridor when you were in school. I'm hoping one day that that's not a true statement, that I can say to a room that you weren't taught people walk through an ice-free corridor. We know that that ice-free area was never actually ice-free. It coalesced, so it's a deglaciation corridor. And the timing of that doesn't work with the current models. There's some newer research that's looking pre the last glacial maximum, which globally was about 21,000 years ago. And so there's some interesting things that could still happen with that. But right now, that model doesn't work. So I'm going to be talking about the coastal route. And that's where Southeast Alaska becomes so important, because we then become this perfect location to identify where people were walking or migrating using boats, vessels of some kind along the coast. And so I'm going to be talking about the coastal route. Really doesn't want to progress the slides. Sorry, I will get this sorted. So if we zoom in then, I'm talking about Southeast Alaska. And so this map also includes the northern northwest coast area. But the area I've been looking at, and I think this is a really old figure, it might be bigger now, is over 40,000 square kilometers. And the interesting thing is the archaeology underwater is very minimally been explored. There's some projects doing little bits of things. So the information about what was there in the past is still just slowly coming out. Now we're working. So I'm going to focus in on the west side of Prince of Wales Island. And you can see here boxes around Chican Bay at the top and the Gulf of Escabel. I love pointing out Chukaka Cave because many people have heard of it. But this area didn't look like this when people would have been first coming to the Americas. I already mentioned the global glacial maximum would have been 21,000 years ago approximately. And Southeast Alaska, they're saying it's between about 19,800 and 17,000 years ago, specifically in this Prince of Wales Island area. So by 14 or 15,000 years ago, the ice would have retreated, but the land was doing a lot of different things. And so we see a very different landscape than this nice modern map. And so if we talk about sea level, things get really complicated and confusing. Is that a nice confusing pit figure for everybody? Lots of random bits. So this is an image put together by Jim Bechtel and his authors back in 2021, and it's the most recent sea level curve. And you'll see a bunch of lines coming down from the top. Those are mostly interior areas. Places like Juneau had higher sea levels during the last glacial maximum and then came down to modern. But on the outer coast, we see lower sea levels. So I find this very confusing, and I asked very nicely and was given a cleaned up version of this. So this one isn't from the publication, but it's based on one of the figures. And he's removed a whole bunch of extra data to make this clear. So what's been left in? A lot of those circles are from the Haida Gwaii data. You'll see that the pretty blue line that we're actually talking about matches that those dots pretty well. And then that solid line is actually the eustatic sea level curve, or the global average. And so when you look at this, there's not a lot of data below modern sea level in blue, is there? We only have a couple points. And so we're kind of piecing together a line and saying, well, it fits with other data, so it could be right. But really, we need a lot more data to understand the nuances, because that is a very steep and fast sea level rise. That may explain why we don't have a lot of sites pre-10,500 years ago. So this includes just south of the northern northwest coast. And I include things north of Vancouver Island because some of the really cool sites on here. So if I take that into a table, you can see dates. These are the mean of the calibrated ages for a number of these sites. And I've taken the liberty of adding, I'm going to say this poorly, Sikan Uti, PET 844 in bold there, which is not dated by radiocarbon. It was dated by the sea level curve, and I've just noticed that I haven't updated that, and that should be 11.4. But this is all the sites that are older than 10,500 years ago that I know about. It doesn't mean there aren't a couple more. They're often in gray literature, but that's it for that entire region. And the oldest is Triquet Island, which is only 13,850. And Triquet Island is a really cool site because they found it in kind of this thing they call a hinge line. So I'm talking about the glaciers and the sea level causing all these different issues. The hinge lines are where the sea level stays the same. And so this is a almost coastal site that would have been coastal almost 14,000 years ago. So we got a lot to learn out there. And that's where this project comes in. So our Submerged Past was developed to go look for caves in Southeast Alaska because on Prince of Wales Island, they've done this amazing job of finding caves that have produced a ton of information about the late Pleistocene and early Holocene, such as Chukaka Cave and El Capitan Cave. And so we built on that to figure out, to try to find caves underwater. But do you know how large this area is? How do we do that? Well, the first step is predictive modeling. And so for my dissertation, I developed a weighted overlay model, and I modified the weighted overlay model to look for cave landforms, so limestone type features and things like that. And that was okay, but I was trying to use machine learning. So I developed one with a random forest machine learning model. And there's a lot of high potential there, and it's a little bit tricky. And so now we're trying to combine things. And then one of my favorite models for other things is a maximum entropy model. So I applied that too to this area. So we take all of that together. I finally get all of this done, and then I get on the phone with Jim Batestel, and he provides me with an actual GIS layer of the limestone and tells me where he thinks I should go, which was way more predictive than any of my models. And my models need to be updated because Jim was way more helpful than the models were. Now, my models do predict the same areas, but my models are over-predicting other areas. So they do need to be refined, and the data we collected on this project will really help improve any future use of the models. And that brings us to our first field season. We went out and we did side-scan sonar and ROV. Side-scan sonar, it's a really great system. It's kind of like aerial photography. You're seeing elevations and depressions, and then you kind of have to piece things together. It's all about, ranging of the sound. The ROV that we rented was actually this little thing called a Sea Drone Inspector, and it actually handled pretty well in the currents, considering how small it was, but both pieces of technology caused lots of technological problems. Despite that, we got 19 survey days done out of the 21 field day seasons. Wow, I can speak. At 21 different locations. And so you can see on the map, I like pink, it stands out. All the places that we did side scan, and then the ROV are these nice little blue triangles. We got 200 gigabytes of side scan data, or 540 square kilometers. And with the ROV, I got about 18 and a half hours worth of ROV footage. So if anyone really wants to look at me driving around the seafloor very poorly, I've got hours of it. It's a great way to get put to sleep. But what I find people are actually really interested in, we went looking for an thing I'd identified in SideScan on 2010 called it's the Restless, which is a shipwreck up near Chicane Bay. And we were looking for it. When I dropped down with the ROV, I came across a rifle. And I went, oh, a rifle, okay. So other people like that. We did not find the Restless. The battery died before we could get it, and we needed to get going. So that was the end of that. But we found a rifle. What else did we find? Well, back when I was doing my dissertation in this area, back in 2010, we did some side-scan sonar in Chicane Bay, and I came across a feature that I thought was a fish trap. And I'd presented it for years, I've published it, and we've never gotten back to confirm it because we had the wrong location when we tried before. And so what you're seeing here is actually a landscape reconstruction of where that fish trap would be on the landscape. And this would be about 11,400 years ago. And this is what it looked like when I dropped the ROV on it, because the side scan wasn't working, so we just had ROV. Okay, I know that's hard to see, so what if I draw the circles in? Okay, can we make it a little bit, can we drop the lights a little bit? You're also blinding me, so it'd be really nice. Thank you. All right, and then if I remove the background, you kind of see some stacked rocks in a semicircular structure. This is 11,400 years old on the ocean floor at 52 meters. It's getting moved around. It's been damaged over the years, you think? So this is Sikan Utsi, which means a rock pile or fish trap of Chicane. So what did we do out of year one other than finding that fish trap? Well, we identified 995 locations on the sonar that year that we needed to then review. The side scan marks were recorded, described, and mapped. Some of these marks were recorded as low potential for caves or were placeholders for other things. So sometimes we were doing a placeholder. So 995 is not, oh my God, that's a feature every time, okay? Like sometimes it's a mishit on the button even. But the initial pass through the data produced 99 potential cave locations. Some of these are very low potential, and 116 potential archaeological locations. What you gotta remember though is that of those locations, sometimes it's the same thing on the next pass, okay? Because we're going back and forth with the side scan. So we could be seeing the same thing multiple times. And so when I mapped these, it became really interesting. So based on the initial review, I had 88 areas of interest for cave openings that were identified within that first year's survey. I tried to incorporate various different things in a ranking system, and which is what you're seeing in the map here. And yes, I know you can't read it. That was somewhat intentional. Pretty colors. So we were trying to locate the best locations for us to go to. So it wasn't just that the imagery indicated something that was really clear, but it also was shallow enough that divers could reach it. That it was within certain distances of town and things like that, so we could get there. So we created this ranked probability, and then we got out there and had the worst weather we had ever seen. And so we basically stayed very close to home the entire time. But I know some of you are here to actually see science, so I put some images together of some of the side scan that I was talking about. I see a nice cliff face there that has the potential to have some openings in it. And you can see the top one and the bottom one are actually the same image. The top one's zoomed in at low resolution, and the bottom one is high resolution. And then we got some interesting rock faces here, and on the left-hand side, I've got some interesting shadows that I wanted to check out. Now, I'm not telling you where these were because I can't remember which ones I didn't have my data to compare. Archaeologically, a lot of what I found was something I referred to as shell middens. So they look like raised features that had scatters of rock. Yes, I know sea otters make them too, but they're not usually raised per se. And so this is 3 examples of that. All right, go with technical stuff. So that moves us on to the year 2 that Christoph's gonna do, and I'm gonna pass to him now, and this will be a fun technological switch. First thing I'm gonna do is go here. Are you sharing your screen or am I bringing up your slides?
I was planning for you to bring up the slides.
Okay. I will escape.
But I can share as well if that's not working.
No, I'm all prepped to do that. Just bear with the laptop, it's thinking.
I can introduce myself already. Christoph Richmond. I'm the Chief Technology Officer for a little company called SUNFISH. And my heritage is a 2nd generation US national, and I have some English and German ancestors. And right now I'm presenting from southern Florida, which was the traditional homeland of several nations, including the Tequesta, the Calusa, and now is the sovereign homelands of the Seminole and Miccosukee. And SUNFISH has been developing underwater robotic technologies for, well, there's a long heritage that I'll go through in the slides once we get them up.
Yeah.
But Kelly came to us, I don't even remember when we started on this. 2020 was it?
I think it was 2019.
2019. Oh, that's right. Yeah, in 2019. She'd seen some of the things that we'd done with our underwater vehicle, and like she said, there's lots of interesting things to see up in Southeast Alaska. So I'll go into a little more detail on what we did then at kind of her behest after she generated this project. And we came in with some of the robotic technologies that we've developed So this is going to be a little more focus on, Kelly knows all the archaeology, and I'm an engineer. I work with robots, so I'll show you some of the interesting technologies that we developed. And the team, so I'm recognizing our field team here in the credits. We had people from all walks of life, students, and we had a couple of divers along with Kelly and myself on this project. Next slide, please. So I'll start off, I can go back one. I'll start off with a little bit of the background of where we even came from and how these robots started off. So we actually have, I'm calling it some space exploration heritage. We started off as a company called Stone Aerospace, run by cave explorer Bill Stone, who developed some underwater mapping and diver propulsion vehicles to carry these mapping instruments, and explored a lot of underwater caves using humans to guide the sensors around. But after some time developing those products, they realized that you could do a lot of this, and you could get a lot of very extreme difficult environment with robots. So following that, we started developing more autonomous robotic ways of doing the same thing, of mapping underwater environments. So we've been to cenotes in Mexico. We've gone to Antarctica. We started building, you see in the middle, this is about a 4-meter, a 14-foot vehicle, weighed 1.5 tons, that we took to Antarctica and went underneath the Ross Ice Shelf. But that was like too big for a lot of applications. So we started taking all this stuff that we had learned about how to explore and map things underwater and put it into a much smaller package. And that's where as we're moving over to the right-hand side, we built a smaller vehicle that can do high resolution, high precision underwater surveys. And we used it for both scientific discovery. So for example, we explored the largest underground lake in Namibia, which is located in Namibia, the world's largest underground lake. And we're able to go beyond where any human explorers had gone before. And now we're also finding utility in more mundane commercial applications, and we're helping to ensure the water supply for people and the safety of underwater infrastructure. So we've gone through kind of oh, and the reason that I put space exploration at the top was a lot the work in bringing the mapping capabilities into an underwater robot was actually funded by NASA as part of their efforts to look for life on other planetary objects that might have water on them. So for example, Europa is a moon of Jupiter that has a large ice-covered ocean that would be an interesting place to go to and explore for life. So that's why NASA decided to fund kind of the work that we were doing. So that's where we came from. And then Kelly got in contact with us, and we can go to the next slide. And we talked about using our current vehicle, the SUNFISH autonomous underwater vehicle, or you'll probably hear me refer to it as an AUV a couple times. So for me in underwater robotics, AUV means underwater robot. It's kind of unique. It's a very highly maneuverable vehicle. I'll show that a little bit. It's small enough to be carried by 2 people, and yet it has a lot of autonomous capabilities. You can use sonar to create 3-dimensional maps. You can use vision, so cameras as well. And it has enough smarts to actually explore by itself and go and map out an area by itself. Next slide. So here you see a little bit more on the specifications and how big it is. You know, it's about I like using metric units here. You know, we try to be scientific, but it's about a 5-foot long vehicle. And it can go down, you know, to depths below what most divers can do. Although certainly not extremely deep, especially if you're talking ocean ratings. And since we put a new battery in it last year, it can go almost 12 kilometers in range. Next slide. And then the way we operate this vehicle is what we call our spectrum of autonomy. So this might sound very engineering and technical, but there's a couple different ways. You know, there's certain degrees that a robot can be operating by itself. Either it can be completely autonomous and deciding by itself where it's going to go and what it's going to look at, and SUNFISH can do that. Or we can script some certain maneuvers that we want to do. We can say, go to this point, then go to this point, then go over here, turn on your cameras, and take some measurements and come back. And it can still do that, you know, by itself. Or then we can add a certain amount of communications, and we do that by using a fiber optic tether. So there's actually a tether that's connected to the rear of the vehicle, which is only transmitting information. There's no power being transferred. But that way we can kind of look over the robot's shoulder in what we call supervised autonomy. So it's still doing its own actions and own behaviors, but we can kind of see what it's doing, maybe tell it to go look at something interesting that we see. Or we can do it completely remotely operated, and we actually have a joystick and tell it, okay, move forward, move sideways. And so this is kind of, this vehicle is very flexible in how it can move up and down this ladder of autonomy. So you'll see in the rest of the talk kind of how we use that to our advantage in this project. Go ahead. So here's a little movie of SUNFISH in action. This is at our test tank in Austin, and it is sped up. Vehicle doesn't move quite this fast in water, but you can see it's highly maneuverable and take, you know, any arbitrary orientation, point its sensors in different directions. This is a little, you'll see these kind of scanning motions in some of the other movies that I'll show. But we like to say that, you know, our vehicle hovers like a helicopter and flies like a jet fighter underwater. Next slide. So we can then use that maneuverability in the vehicle to build some more complex behaviors. And so we've done some things like the vehicle is doing these scanning maneuvers, and then you'll see this white area in that tunnel. It's decided that area is safe for it to move into. Or here it's doing, this is in a simulation, the previous was actual data, but here it's mapping out an area and deciding how to move through it. And so we've done, for example, you know, this is a natural cave in Florida that the vehicle mapped out, and you can play back the data and you know, feel like you're flying through that tunnel underwater. So those are kind of the basic capabilities of the vehicle. Next slide. And then we've also added a couple of other, you know, things, and in particular for this project, we tried to use, you know, you could have a complex underwater vehicle that has some arms or something to do some sampling. But SUNFISH is, you know, agile enough that you can just stick a stick on the front of it and precisely position that. And so, for example, here we added a little sediment sampler to the nose of the vehicle, mostly as an engineering demonstration to show that, you know, if we can get this robot into some very remote underwater location, we can actually bring something back that would be of scientific value. So next slide. Oh, cool. Yes, there you go. So yeah, you'll see how big it is. Doesn't get a great big sample because the vehicle doesn't have a lot of payload capability, but you know, we can bring something back that nobody else could see. So Kelly talked a little bit about, you know, what the goals for this the second year exploration were those sites, those target sites that were identified in year 1. We wanted to verify which ones were really caves or rock shelters, and then map them out and take some samples from them. And then Kelly will talk about what we do with those samples. So next slide. And specifically for the robot, there was kind of like 4 steps that we wanted to do. So there were the targets that seemed like possible good, a nice cliff that looked like it would have some openings, or we see a spot that we want to look at closer. So confirming those with the robot, and then doing this 3-dimensional mapping that I was showing you, and looking at those spots in more detail. And then if we find a cave, or when we've found a rock shelter, seeing if there was some area that might contain sediments that we could then, as the last task, go and sample, either with divers if we needed a larger sample, or like I showed you, the small sediment sampler on the vehicle. Next slide. So we went out in May and June of last year, 2023, with our vehicle in beautiful Southeast Alaska. And you can see it's, we used a fishing vessel, the Showtime, running out of Klawock. And, that's pretty much all you need is the robot. And you see over on the right-hand side some laptops. And you can run this vehicle, off of kind of any vessel of opportunity. Doesn't need to be a big, dedicated science vessel to do some fairly sophisticated robotics work. Next slide. But we did run it in what I was talking about, the supervised autonomy mode, which did mean that we had this green line attached to the back of the vehicle, so that we could get pictures and the sonar data back. And in this kind of complex environment, and we wanted to make sure that if there was interesting things, that there was a person there to confirm or to pick up on it, and make sure that we really didn't miss any interesting scientific targets. But that meant that our dedicated techs did stand outside in the rain sometimes to handle this fiber, which was a kind of a manual process. But I think overall, that's part of the field work is getting this stuff done. Next slide. We also had, Kelly mentioned a couple of divers, 2 divers on this project. And they were there both as, supporting the robot in case there was any problem, with the hardware. And then also to be able to record what the vehicle was doing. We wanted to be able to tell everybody the story of, get great pictures. And you'll see some of those later in the talk. And to be able to actually get some science. So to do some of the sampling that our robot was too small to do in areas that they could get to. Next slide. Oh, and I guess you can see the, cold water, full dry suits, and the divers we had are some of, the top cave divers worldwide. So they had full rebreather sets, and, they were able to go into pretty much any place that was shallow enough that our robot could. If we did go to any deeper sites, that would probably have been out of their diving range. So we enjoyed some great summer Southeast Alaska weather. I forgot to actually check again what the exact numbers were. Maybe Kelly remembers, but I think we had out of the 22 days that we were there, was something like 15 or 16 small craft advisories, which was kind of a disadvantage into being able to get out to some of the more interesting sites. But, we managed to work through that. Next slide. And, we did enjoy the beautiful Southeast Alaska scenery, SUNFISH, transiting through, I think on the left there, that's Vita Bay. and coming back towards Cloac, looking over our little mission control network box. And last slide, I mean, some of the scenery is just stunning. So this was definitely a big bonus for me of doing this project. Next slide. So what did we actually get from our robot? The first thing was a 3D point cloud, we call it. So this is basically just all the points that the sonar on the vehicle took, mapped out in one big cloud. But you can see what the what the shapes, the underwater shapes already look like. So on the upper right, you can see a little bit of an overhang. Some of these are, these are all different scales. So in some places you see more detail or less detail. But this is all kind of the raw sonar data. And we could get up to about, 5 centimeter resolution on the things that we could see. Next slide. And then the other thing we could do with the vehicle was, so this is a screenshot of actually the live view that we had back at our control laptop. So this is SUNFISH. It's made a map of a cave that it's navigated through, and then it's up for there on the right-hand side. And here we've told it to go back to this little white dot that's on path. This big blue, looks like a big blue pipe that goes right through the middle of this cloud of points, and is free of any obstacles, and it's deciding how to move back through that map. And then the next slide. And then when we get back, we can actually take these point clouds, and we call it meshing, but you create a surface. And this is the actual three-dimensional map then. So for example, this is a rock shelter, or on the next slide, this is an example of a cave. So on the upper left, on the upper right, we have a little bit bigger overview. And zooming in on the left-hand side, you can see some of the details of this cave that the vehicle was able to go into and map out the insides of. Next slide. And then, so we've gone to the whole point of identifying caves, looking and finding areas of sediment in there. And then we had an interesting problem where we wanted some of these sediments to be sampled by the divers. But how do we explain to a person on the surface where something that the robot saw underwater is exactly? And we actually had an instance, for example, we wanted to look at this rock shelter that's on the right-hand side. But the divers we figured out after everybody came back up, had gone off to you can hardly even see it on this map, but a much smaller ledge looking out that didn't seem to be the right target at all. So on the next slide, we actually managed to use the robot then as kind of a diver assistant, and it knew where things were in its map. So for example, you see the yellow cross in the vehicle map. Well, the robot could just drive to that location and show the divers, here, this is the point that we picked, and then kind of watch them. There's a camera on the front of the robot, and it could watch the divers and record, this sample was taken in this location. So using kind of the best parts of both the robot capabilities and, the human capabilities to do this very interesting science. Next slide. And then finally, we were able to do a little bit of autonomous sampling as well. This was, I would say, mostly an engineering demonstration, because as you can see, there was a diver here to record it. But this is an example of, the vehicle had mapped out this area, and we told it, okay, take a sample at this location, and it automatically knew to rotate there and drive and ram that sampler right into the sediments. Sorry, little cucumber. So this was really a great, demonstration, engineering-wise, of some of the capabilities of this kind of robotic technology in these kind of very unique and difficult to get to environments. All right. I think that's got the next slide. So I've got my acknowledgements up here already, and I know we'll have more at the very end of the talk, but I wanted to thank the whole field team, in particular the people of Southeast Alaska for the access to this very interesting location and all the support that we had in figuring out this interesting part of the geology and archaeology that hasn't been seen for thousands of years. So I'll hand it back over to Kelly at this point. And thank you guys.
Thank you so much, Christoph. That was great. Bear with me a second as I switch things around. Sorry, it's a little slow, it thinks. Here it comes. There we go. So I'm going to keep going and talk about the core analysis, which that lovely lady who stood all that time out on the deck also figured out how to split the cores for us. We used 3-inch PVC pipes that were about 3 feet long, and the divers used a kettlebell to hammer them into the sediments and then cap them before they pulled them out. We got 4 cores, 3 of them down in the little south corner there where it's nice and sheltered to deal with the weather that we had. So we spent a lot of time down in the Ladrone Islands, and then 1 core over on San Fernando Island, which Christoph showed you, was the location where the divers took the core, not where we asked them to, but it's still a really cool core. In addition to the 4 cores, the divers collected a bag of sediment from the back of that cave, Sea Lion Cave. And I'll talk more about that. And then, of course, we got the little sample from SUNFISH. And for those of you here, you can come up afterwards and see it. I'm a little sad. I didn't realize until now with the video that the video we show doesn't have the little ball pop into place on the sampler, which is how we keep the sediments in. So what did we do? Well, first off, we have pollen analysis. And no, these are not this is from samples. So pollen was done by Dr. Nancy Bigelow from UAF. Dinoflagellite cysts by Dr. Vera Pospolova from the University of Minnesota. I did microdebitage analysis with comments and feedback by Dr. Lisa Sonnenberg from Lakehead University in Parks, Canada. So we got a fair bit of information. We also did radiocarbon dating and Bayesian analysis on the radiocarbon dates. So when we look at these cores, we've got some interesting sediment transitions. And what I'm trying to do now, and you're going to have to bear with me because it's my first attempt at it, is I'm trying to put the story together about what we learned. So I'm just pulling in all of the analyses. And the first piece of the story that we've learned about was the ages. And so that middle core, core 3 there, if you look at it, at the bottom, it says 10,690 cal BP, and then it gets younger, which makes sense, 10,472, and then it gets a lot older at 11,967 cal BP. So we've got a lot of mixing going on with these sediments. I do want to note that the radiocarbon dates are marine corrected. That comes up a lot, and we followed Schumacher's et al. 2021 methods for that. So I took one of the beautiful videos that our diver, Tamara Adame, shot of Sea Lion Cave. So you can watch that while I explain to you Sea Lion Cave. So I'm going to tell you the story of Sea Lion Cave, and it starts off with the fact that it is actively used by the local diving community. I asked some questions of retired Forest Service archaeologist Terry Feifeld, who then said to me, "Oh, I know that cave. I did my dry suit cert in it. It's called Sea Lion Cave because at some point somebody found a bone in there and they think it was a sea lion bone." Our divers love this cave to some extent because the seals would come and swim with them. I'm sorry I didn't find that video, plus it's not long enough for me to tell the whole story. So this cave is at about 20 meters depth. the opening of it, which means it was inundated around 11,000 years ago with our current sea level curves. So I told you, there's a sample from the back of the cave, which is microdebitage. Well, that has microdebitage in it. I have samples from the entrance of the cave, which has microdebitage in it. Here, let me see. Okay, so that one's from the back of the cave. That kind of looks like obsidian to me. I'm working on cleaner pictures of that one. This is from the SUNFISH sample from the entrance to the cave, and we've got some nice flake-like features here too. So on the bottom left, you can see a platform. On the right, you have a platform, and then it actually tapers off like a flake would. And then this is from a core that the divers took out in front of the cave. The image on the right, you can see a nice bulb and platform, and it's very flake-like. And then I take pictures in groups because I have a whole lot of little rocks in front of me, and I can't see them until they're under the microscope. But in the bottom left figure is the bottom left figure. The top right rock looks very flake-like, but you can see not all the rocks look that way. And in the top image, the left one has a beautiful bulb on it, but that's questionable. And that's the catch. Some of this stuff is very questionable. What else happened here? For the dinoflagellates, overall, the sediment samples suggest a dynamic environment with periods of high productivity, likely driven by varying nutrient levels and possibly changing light conditions. There's an increase from autotrophic to heterotrophic ratios towards the top of the core, indicating a shift in conditions. So we're seeing environmental change. Still working on pulling this all together to make this all make sense. The pollen is dominated by hemlock, followed by spruce, alder, and pine. Fits the region. So we're starting to see that story. Oh, sorry, there's the pollen graph. I like this pollen graph. It's short enough that it actually is almost legible on the screen. Let's use this as an example to understand pollen graphs, though. So the species across the top, varying quantities across the bottom, and then the depth of the core. Only one sample from that core was taken. Unfortunately, that was our first core, and the divers and I miscommunicated, and we flipped the core over a couple times, and so it was mixed sediments because it wasn't a full core. So it's basically one sediment pile, so we only did one sample from it. So we've learned something. We learned about this, and if this was inundated 11,000 years ago, we only have marine sediments. Let's go over to the Ladrones overhang. So Christoph showed that beautiful image of sunfish watching as the divers took the sediment cores. He had some beautiful images of that nice little overhang, and you can see the picture of it too. This is a very complicated environment, but it's just around the corner from Sea Lion Cave. At the very surface, we do have the Alexandrium diatom, so it's a hab-causing species. And most likely, it's the cysts aren't preserving, which is why we're not seeing it through the sample. But we're talking about a mixed sediment, very mixed sediment. If you are looking at those dates, you're noticing a whole bunch of reversals. And I've been racking my head about this for like 6 months now, going, what is going on here? And I think it's related to the size of the shelf in the area. So we're going to be in the wave action area. So you see the wave base in the middle of this image. Based on average wave height in the area, I've calculated that it's usually, waves affect the seafloor down to a depth of 38 meters. Well, this location's at 22 meters, so it's within the wave action. So until enough sediment gets in there that it stops mixing, it's always gonna be mixing the top so many inches of the sediment. So these sediments that are buried, maybe, until the sediments are properly buried, they're getting mixed with the layer above them. We're starting to discuss, Lisa and I, who's also a geoarchaeologist, we're discussing that there might be an erosional event here between that light brown near the bottom and the greenish brown at the very bottom. And that's why we have this shift to a different layer. I want to talk a little bit about that 12,000 year mark. If that really is a true date of 12,000, that would be, oh, sorry, I have microdebitage in this one too. Microdebitage has been found in multiple locations in this core sample. So that means we probably have an archaeological site here at several different depths. Okay, 12,000 years ago. That would be 145 meters below sea level. So I went and grabbed one of my old sea level maps that I've put together, and this is what Prince of Wales Island would look like at 141 meters. Okay, so estimating. The Ladrone Islands are a little dot in the middle, but you see, so you see the Long Island, because I can't really point where anyone can see with anything because of the difference in web versus here. But you see how there's this deep trough coming up above what is Sumez Island. Let's see if I can point a little bit. So you see this deep trough coming through here. Well, the Ladrone Islands are over here. So there's a deep channel running through here. Well, that's gonna start making sense. And so I apologize that the map was made for another purpose. But dinoflagellates are saying that this area at this time period roughly has the first instance of, and I'm gonna say the cyst wrong, Hinianosea matascuska outside of the estuarine environment of neighboring British Columbia. The pollen in this area at these depths is dominated by spruce and alder with some fern spores. The pine slowly increases as we get younger. She also found spruce needles and Pinaceae seeds, wings, fragments in it. So this fits with the other pollen reconstruction. So 12,000 years ago, this is what we're seeing. So this is the base of the core. So this looks like a deposition, and the base of the core looks like a depositional environment in a nearby shoreline. So that fits if it's around this depth. And you've seen that sea level curve where it goes up very steeply. 12,000 years to 11,000 years is a huge difference in how much land is available. But in a place that's very protected and sheltered like the Ladrone Islands, it's not a big change. Here's the Ladrone pollen, which I know you can't read, but it looks pretty to me. I already talked about the base of the core. The middle of the core, we start seeing pollen from both western hemlock and mountain hemlock increasing, and a reduction in alder and fern. And then at the top of the core, we see a decrease in western hemlock along with an increase in pine and alder. So, as I said, I'm still trying to figure out what all of this means. But we're starting to put the storyline together of what this environment looked like. We do not technically have terrestrial sediments at any point in these cores. We have 12,000-year-old dates, and we have pieces of rock that look like they could be microdebitage. So we have sites, we found caves, we mapped caves, so we've met our goals for this project. And what are our next steps? Well, we have to write this up. You're our first presentation of these results. And as I said, still trying to make it all make sense, partly in my head, and we need to get these results together and published. I'm also applying for more NOAA funding to go out because, as I said, I had all those potential archaeological features, and I'm looking to go out and test some of those and see if we can confirm some more archaeology on the coast. I'm gonna throw the acknowledgement slide up and say Gunesh Chish, and I'll leave it there if there are questions. They want the microphone.
Here we go. Thank you. Questions? Oh, hey.
What does microdebitage mean?
I should have explained that one, sorry. So whenever you use a stone tool or you sharpen a stone tool, little flakes break off, and they're very small. I'm working with stuff that's less than a millimeter or around a millimeter and smaller in size. And so these exist whenever you use or make a stone tool. And what Lisa Sonnenberg demonstrated through some work in the Great Lakes is that you find these in a specific area around a use area. And so by identifying these, you can identify places people did things, but they didn't leave the full stone tool behind. Sorry, I knew I was skipping steps, and I was trying to figure out which steps I was skipping, so thank you.
Any other questions from the audience? Yeah?
You're talking about the technology that you have, and I guess my question is, do you have anything like a ground-penetrating radar that works underwater so you can see what's underneath the sediments? Because this is a terrain where you have sediments that might be hundreds of meters thick in some cases.
Yes, completely, and I'm really excited that in less than the 3 feet of that PVC core, we hit 12,000-year-old. But yes, there is something called sub-bottom profiler, and that's part of the next proposal is we'll be doing additional sub-bottom profiling work. But I have some sub-bottom profiler data from the Gateway to the Americas project, which is way more than I can cover in this talk because we had other things. Yes, and it's actually pretty good, and they're doing some great things. And I highly recommend a presentation about 2 weeks ago for the NOAA library. It's on their YouTube page about the Channel Islands, where they talk about that technology, and they talk about some newer technology that they've created too. The NOAA, NOAA library.
So this is a question for Christoph. I'm assuming you helped work with the SUNFISH. As a software engineer, I'm really interested in what kind of models and programming you use to get it to run autonomously through these caves that it is actively mapping out.
Okay, I think that question was for me.
Yeah. Could you hear it?
Okay, no, it was kind of breaking up for me. If you could repeat.
Yes, if we could turn them up though, Misha. You should be good.
Hello. Okay. Could you repeat the question for me, Kelly?
I can repeat the question because he can hear me, unfortunately.
Okay.
He's asking what kind of software you're using because he's interested in the programming to create the autonomous.
Yeah. So the robot itself, it has a couple of different kinds of software, but the core system is something that we wrote ourselves, but based on the robot operating system, ROS. And like as far as languages, we actually mostly use Python, which is used in a lot of different areas these days. And then I guess some of the processing software, that kind of created those meshes and maps was actually open source libraries. We used OpenCloud. Now I don't remember what the library is called again, off the top of my head. But there's actually some very good, open source tools for working with that kind of data as well.
Does that work? I'll put you guys in touch for more. I'll put you in touch for more.
So
Yeah,
we have a
definitely.
couple
I don't know
questions.
if I have my contact information on here, but yeah.
We have
Feel free to
questions
email me.
online. This is from Marjorie from Seattle. And when do you expect to go back and explore more?
When we get more funding. At this point, if all goes well, I'll be back out in the spring of 2026. The funding process is a very slow process. So the proposal's due again in October, and by the time everything works out, it'll be a couple years. So there's a bit of a lag between projects and between field work sometimes.
Okay. There's another question from Auk Bay from Adventure Fishing Tours. And what do the platform and flake tell you exactly?
If I'm right and they are actually flakes, microdebitage, that means that humans made them. It's the distinct features that we see on flakes are not produced naturally in the environment. Now, one flake doesn't make a site to most people, and there's not just one flake in any one of these locations. So it means that people were there. It's just still working out in my head how people were there and were underwater. And so that's why we're talking about erosional environments and transportation. And so, as I said, we're sorting this out. We're not completely understanding, but we do have sites.
Okay, one more question from online, from Buster Landon. What was the scale of the rocks that were in the Oot that you mapped? The cave, I guess.
I have those numbers on a slide. I just don't have that slide with me. I believe the entire, the side scan image was actually that they were about 30 centimeters high. So each one of those rocks is kind of like small boulder size, about 30 centimeters or so, about a foot. And some of them are smaller. So it's very standard to what we see with stonefish traps and weirs across Southeast Alaska. Thanks, Buster.
Any more questions? We have another question from the audience here.
Okay, obsidian often has a chemical signature and you can trace it back to a specific site. And I was wondering if it would be possible to trace the origin of those obsidian flakes and if there's any obsidian in the local area. Because if there isn't, then that alone is an indicator that it was brought in.
Exactly. And yes, I've got to have some nice conversations with either Jeff Rasick or Rudy Reimer and see if anyone wants to play with my little bits of rock. But we're also talking about things that are very small. Lisa confirmed with me that we should still be able to do portable XRF on them. And Jeff Rasick has a beautiful database going of the obsidians used throughout the region, including all the way into Alberta. And yes, there is obsidian in Southeast Alaska. Shukakaa Cave had obsidian, and they've sourced that. And so we've put a lot of information together. But Sumez Island, that oddly curved one, that relatively small, just southwest of where we were, has an obsidian source at Arena Cove even.
Yeah, that was one of the obsidian sources from Shukakaa Cave. The other one was Mount Aziza. Yeah.
Is any of the pollen that you found from plants that are no longer here?
I do not know, but I will try my best to follow up and make sure we answer that. I don't believe so. That wasn't brought out in the report from the pollen analyst from Dr. Bigelow. So I don't think so. It's pretty common stuff that she was identifying. It's just that one dinoflagellate that they've only ever found in marshes in BC that was unique.
Another question?
Thanks. This is fantastic. I appreciate so much what you're offering. I was just curious, given better weather conditions, what you had hoped to find and how much further you might have been able to go with that.
I really wanted to get out of the Ladrone Islands. Really wanted to get out of the Ladrone Islands. You notice all my stories are from the Ladrone Islands. But we only had a couple days where we tried to go out. And one day we went out and basically nobody wanted to go out on the boat again after that. It was so rough. Because, well, there's only a smokecraft advisory in this area. Can't we go that way? No. My main thing that I've been trying to look at is Sea Otter Sound. And so getting up there and getting into more of the bays in there is one of my goals. And we've got some great data from year one in that area, including some absolutely amazing potential locations. And we just couldn't get up there. We got up there one day, I think it was, and we still had to stay as sheltered as possible. And so it's all a matter of timing that weather, and we did not get it right that year.
Thank you. Hooray!
Thank you, guys.